Hi, and welcome to another exciting edition of C Programming. My name is Nate Nessler, and this is for Hyperactive Studios. Alright, so before we kind of looked at some voltage and some current and some resistance types formulas, but what we haven't looked at is how can we use all of them together in the same program. And probably the best way to do that is to use if condition statements. So that way we can choose between which one we want to do. We're basically saying if the person wants to find voltage, use the voltage formula. If the person wants to find current, use the current formula. If the person wants to find the resistance formula, find the resistance formula. Use the resistance formula. So you kind of get the idea here. It solves several problems. And what I did is just took this find voltage from before and I have added to it. So instead of just having just the voltage function in here, and here I have declared it. I'm now declaring one called current and one called resistance. You'll notice it's almost identical to voltage. So if you just copy and paste this one right here by selecting it, and then say Control C, then Control V to paste it, and you'll get the current, and paste it again, and change it to current and to resistance. And then we have double NV here for voltage. And then we also have the double NR for resistance here under the current one. So in this way we're passing in for resistance, and double NI for current again. So we also need a menu. And as before, when we wrote up our voltage one in our previous one, we had the ability to ask them to input the current and then also input the resistance. Well, we need the same thing here for the current menu. We need to let them input the voltage and input the resistance. And then for resistance, we need to let them input the voltage and input the current. So we need menus for each one of these. And we already have our voltage one from before, so we're just going to copy and paste our code from our previous main into our voltage menu function. And then we need an overall function to determine which one they want to solve for. Do they want to solve for voltage, for current, or resistance? So we need a menu to let them select which one they want to solve for. All right. So you notice the voltage is the same as before for the way it is defined. And note this is declaring versus defining. So if I just copy and paste the same formula over and over again, and then make my slight changes. So then we have NV here and then NV here for our voltage, and then name it current, and then name this one resistance, and then you have your NV and your NI. So you have your NV and I like that for both of them for resistance. All right, and then our voltage menu, you'll notice, is identical to our main function that we had before. So we have our double V equals 0 semicolon, double I equals 0 semicolon, and double R equals 0 semicolon. And this makes these variables local to this menu. And these variables don't exist in the program until this menu is run. Essentially, we're doing our calculations and our input from this menu and the output of the result. So for this reason, we don't need to basically define the variables in a global program to then pass them in. We can just define them directly in here, and then they don't have to take up memory until the moment we need them. So it makes it a little bit more efficient. Printf here, of course, enter the current, colon, close quotes, close parentheses, semicolon. That lets us display that message. And then we do a scanf, in quotes, %LF, close quotes. The L stands for long float. We do have to use the L when we're doing the scanf versus when we're displaying. Note I did the %.3 here, F, in order to make it do 3 floating point decimal values for precision. Comma, and then we do and I here for ampersand I for our scanf. Then printf, enter the resistance, and we need them to enter the resistance. So this stores the value into our current for our I. And again, this ampersand here is for the memory address. It points to it in memory. And I can show you this actually. So Well, I'll tell you what, I'll talk through it here and then I'll go back through it while the program is running and showing how this works in memory. But yeah, this points to the location of the value in memory for this variable and stores it there. And I'll get into this more depth when we run through the program and step through the memory of the program when we run debug mode. Printf here, enter the resistance, colon, close quotes here. Make sure we put that space so it doesn't smack up the value up against this colon here. And then a scanf here, open quotes, %lf, close quotes, comma, ampersand r, close parentheses, semicolon. Again, this also points to the memory address for r here. And I'll get into more details about scanf here. V equals voltage here, open parentheses, I, comma, r, close parentheses, semicolon. And this is going to be passing in I and r for a voltage for a calculation, so we get the voltage returned as a double. And then we're just going to print out what the voltage is. So the voltage is %.3f here, volts /n, makes it go to the next line. And we replace the percent here, .3f, with the value inside of v, and we're going to floating point 3 positions for your floating point decimals. So this means decimal 3 position. Current menu. All right. It's the same as voltage menu. Copy and paste. Then come down here and change it to VR here for this. Say enter the voltage along with enter the resistance. And then put in the formula for current, and then make sure you put current here. That's it, and then also say current here. It's basically identical to what we just said. It's just now for current, and we just got to replace the things that are required for current. Paste again, and change this to V and I, and then have V and I here for your resistance, because the resistance formula returns to resistance. Put your R over here, and then say resistance here. So, just replace that, go through and replace that. Oh yeah, also you need to say ohms here for resistance, and you say amps for good old current. Okay. And then our main menu. Now this one's really actually different. And we need to write a message. And this is going to be the first thing that the person that uses the program sees. It's going to be the menu function. So I'm going to say select which one you want to solve for, :n. And we're basically displaying to the screen. And then we're going to display their different options. Solve for voltage would be 1. Number 2, solve for the current. Number 3, solve for resistance. Make your selection 1, 2, 3. Which one do they want to select? I'm going to create a new variable here called n. So I'm saying int n equals 0 semicolon. And then open parentheses, open quotes here, %LDF, LD, close quotes, comma, and IN, close parentheses, semicolon. And again, this points back to this memory address here for this variable. We initialize the variable to 0, and I'll show why that is in just a bit. Kind of important. If we don't do that, it is a problem. So, you can see here scanf is going to receive that value, store it into n for whichever one they type, and we need to test. Alright. And then you've had some people ask me, well, how do you do it with a double instead of an integer? Well, you want to do it with an integer. Because you can just select 1, 2, 3, etc. in these whole numbers. I'll go back through here in a second how to do this more complicated if structures like this. And it brings up a good point, and I just don't want to get into it at the moment, but you get the idea. And I'll explain all about the ifs here in a second. So if open parentheses in space equal 1 close parentheses. What this is an equivalency check. We're checking what the value is inside of the n variable in memory while the program is running. And we want to see if it matches 1. If it does, then it's going to run the voltage menu function. If it doesn't, then, well, it won't. Skip this and go to the next one. And that's basically what this all is about. So if this matches and it comes out true, we do the code inside our if block, stored between our open and closed curly braces here. And if it's false, we skip that one. We go to the next one down below it. So else if here, open parentheses, in space equals 2, close parentheses, does a check against n. Is n 2? If it is, then we can say do the current menu. So if that's true, if it's true that the value inside of n, if they typed in 2, then it will match 2, and then we'll have current menu gets executed. We have our open and close curly braces like so. Else if here, n space equals 3, close parentheses, open curly brace, resistance menu, open close parentheses, semicolon, close parentheses, not parentheses, but close curly brace. This is if they entered in 3. Now, if they entered anything other than 1, 2, and 3, we use our else and we say you must use the numbers 1, 2, or 3. So that kind of makes sure we have like a catch-all on that, which is cool. Okay, awesomeness. So we have our main here. Int main, int arg, and then char star star arg v is the arguments that are going to be passed into our program. We're not accepting any right now, but if we did, we could by doing this. And then we have our menu is being executed. So that's this whole menu function right here. We're going to run it. And then we're going to return an exit status of 0 that is successful. And that's what this exit underscore success means. It's a special constant that was declared with inside of NetBeans that means that it successfully ended the program. So I'm going to tell it to stop execution on this menu, and I'm going to step through this code and kind of break it down and explain it further and better as we look through different values in memory as they execute and why things are doing what. Alright, so I'm just going to go ahead and hit debug, and we are building, and let it go, and there we are. Okay, so now we're on menu. Now I want to dive into this particular one here, so I want to step into this function. If I step over it, I won't do this function. I'll just go to the next line of code, so everything inside the function will happen, and then let's get to an exit return status. It's not really what I want. I want to step into my function, so I'm going to say little down arrow here, and it's going to step into menu, and now we can see our menu. Now I'm going to step over this menu bit by bit. Now the awesome thing about this is that as I run this, I can actually see different values here happening. So let's just say step over. You can see the messages appear for the printf as I step over each one of these statements. Solve for the voltage, 1, 2, solve for the current, 3, solve for the resistance. And you notice I didn't do a /n at the end of this. Why? Because I want to be on the same line with scanf. So there we go. And then int I is going to exist now. And then we're going to read that into memory. And now it prompts us for our selection. So let's just do, well, we did essentially, let's do 2. Alright, if, now, and this is kind of cool, I'm going to right click on my n here, and I'm going to say add watch. Well, I don't have to, it just automatically popped up. And we can see all the different variables that are in scope or out of scope, and n is in scope. And it has a value of 2. What in scope means, it does exist inside this function. So it's just within the scope of this function, aka it's part of this function. So n is set to a value of 2 because I typed in 2 earlier on my output. I'll prove that. See, I typed in 2, and it got stored into my n variable here. So that's kind of cool. And all I did is push on output like this, back and forth. It lets me switch back and forth between them. So when they type this in, this is this location in memory right here. And you can see that it exists in RAM. And so when we're saying ampersand here in, we're saying store the value that they type at the keyboard. Now it continuously checks and looks and looks and looks for everything they're typing on the keyboard until they hit enter. Once they hit enter, this is how scanf works, it then returns those values. In this case, we're saying %LD. Now remember, D is what's used for integers. And we must have the long in front of it for scanf. So that's the way it has to be. So when we say %LD here, it's going to make sure that it comes back as an integer for whatever they typed at the keyboard. Now that it comes back as an integer, instead of assigning its value back to to a variable or returning something, it doesn't have to. Instead, it's storing it directly into the memory address where the end variable is. So instead, it puts 2 directly into this variable's memory location and thus assigned it. So it's essentially like the same thing as, well, actually, it's not quite the same thing as assigning it back to the original one. That'd be making a copy in memory, like say up here, something like that, and then copying that value and placing it into this memory address is the way it is when we were saying one of our functions and returning a value, like when we did voltage. That's what's happening there. We're actually we're making a duplicate storage point in memory, and then we're copying that value and putting it into the variable that we're assigning it to from the equal signs. This skips all that. What this does with the ampersand end here is that it actually just puts the value directly into the variable in memory. So this is faster. This takes less memory and is quicker for its execution. So that's why they're doing it that way. A little more advanced here as far as explanation. It gets into what's called pointers, where we point to the location in memory for a variable. But that's the way C is. C doesn't hide anything, and so you're kind of diving right into the depth of the program right away. So, but what we can see here though now, when we do our if check here, is n is 2, right? And is 2 equivalent to 1? Well, no, 2 is not the same thing as 1, right? This is what this equal equals does. It doesn't assign the 1 to n. It checks to see, is it equivalent, right? So, is 2 equivalent to 1? Is 2 the same thing as 1? The answer is no. No, it's not. So, it's going to skip this if statement, like it's definitely going to do it. I promise you that. So when I say step over here, it is literally going to skip this voltage menu and go to our next else if. Alright, bam, it did. Now, check this out. N is equivalent to 2, has 2 stored in it, right? So is 2 equivalent to 2? Meaning, is 2 the same thing as 2? Yes, 2 is 2, right? We can all agree on that, I hope. So in this case, we're not going to jump down to the next bit of code here. Instead, we're going to jump into here. Now I want to point this out. We're also using else ifs instead of just a series of if statements. This is if statements. Even after it finds what it's looking for, it'll keep looking for the other ones to see if any of the other if condition statements match the conditions. However, else if says, if not this, then do this. So once we do this one, it's going to skip all the rest of the code that's in our else if structure and jump down to the bottom of the function. It won't keep looking for something that it's already found, basically. So there are certain circumstances where you want to find where you do want to do all the if tests all the way down the line, one by one, one after another. But there's other times where you don't, and that is if you have something that can be tested true in several different circumstances, where you can have something true and you need all of them to do their different things, then you want to do a series of if statements. If, however, you're doing a whole series of checks and it can only be one thing, then it makes sense to use else if, because it means everything else is going to be wrong. So it doesn't make sense to keep looking to checking if something is right when you already know that you've already found the right one, and otherwise you're just checking for something see if it's right or not when it's already know that it's wrong. So it doesn't make sense to do that. And that's what we have here. It can only be 1, 2, 3, right? Or some other thing that's not supposed to be the right one. So if it's 2, it can't be 3. And if it's 2, it also can't be 1. So it doesn't make sense to keep checking and see, hey, did they type in 3? Hey, did they type in 4, 5, 6, 7, 8, 9, 10, whatever they typed, right? It doesn't make sense to do that. So that's kind of the deal there with all that. Alright, so that's why we have it set to that. Alright, so we have current menu here. And there's that. Alright, so now it's going to jump into here. So if I say step over, it's going to pop right here. And now I'm going to step into this function. I don't want to step over the function, I want to step into it. Now check it out. V and I and R have crazy values in there. Why? Why all these crazy values? They're weird, right? Well, the deal about this is the reason why we have to initialize our variables is because essentially we're grabbing these variables from memory from the operating system. The operating system issues us RAM to use. And these variables, RAM, existed from, say, some other program was running beforehand. And it could be anything. It's just up to the operating system how they serve out the RAM to us. It could be coming from anywhere, basically. And so you're unlikely to get the same values twice. Very, very unlikely, because the operating system will do whatever is best for the computer and not serve necessarily the same thing over and over again. So we're just getting these random values in RAM that were sitting there from the previous program. They were never cleared out, so they're just filled with junk. So that's why we have to initialize our variables to some value for a starting value. Otherwise, we have some crazy value in here. This will really mess with you if you don't do this. If you don't do this and you don't initialize your variables, and you just end up grabbing whatever value is sitting in RAM ahead of time, say you go to add or do something, some kind of mathematical function, and you forgot to set it to 0 for a starting point. You get these random crazy numbers every time you run your program, and you just can't figure out why it's happening. Well, the reason it's happening is because you forgot to initialize your variables. You forgot to assign your variables a starting value. And so instead, it just has this random garbage values coming into it from RAM when it first got allocated to RAM for these variables. So that's kind of what's going on there. Not kind of, that is what's going on there. So when I initialize this, you'll see them change to 0 one by one here. So watch this. Bam, there's V, right? V was the first one, set to 0. Notice how the line has to go past the actual line of execution before it actually happens. So it means that now that we're down on this line, the one above it has been executed. Now we're about to do this one with double I equals 0 semicolon, but it hasn't been done yet. That's why you have this crazy number value here. So I'm going to say step over, and bam, now it's 0. So check it out. Here is our resistance with R, and we're going to step over that one. Pow, there it is, 0 on that one too. Great. And then we're going to ask a question. Enter the voltage. Okay. So I say step over that. You're like, oh, didn't it disappear? Yeah, it does. Not yet. You might be going, what? Well, the scanf kind of holds it from being displayed on the screen until it executes. So that's kind of the deal. So now that scanf executed, now it will display the enter voltage. So it holds back the execution of the display of the message from Printf, only when followed by a scanf, apparently. So, all right. So let's type in a value for voltage. I don't know, like 30.01, for instance. This is going to bring up another issue I want to show you in a second here. All right. So that got stored, and so now it's stored in memory. And I'll show you what happened here. And so there we are, 30.0102. Might go, what? You didn't put that in. Yeah, I know. I didn't put it in. There's a problem with computers for storing values, variable values. The values are actually, well, there's some precision lost on them. You get some variance on them when they're stored. It's no way around it, really, on floating point numbers. This is only on floating point numbers, like doubles and floats. You're not going to have this on integers or booleans or anything like that, but on your floating point numbers, yes, there is a little precision inaccuracy. So this is what rounding up helps or whatever. We have a larger precision, so that helps deal with that. But essentially, when you store the variable, the value, it's not going to get stored as you type it or as you told it. Or even if you're not typing it, right? If you're signing it in your code, same thing will happen. It just doesn't matter. The same thing's going to happen. It's a precision loss that happens when you store something in RAM. You're always going to have some precision loss with a floating point number, a decimal number. There's no way around it. But it's very minute on this. It's way far out there. And if we do a rounding or precision to a 3 decimal places when we display it, this will just pretty much be inconsequential. So it won't matter. But yeah, there is some precision loss introduced into your numbers when you're doing mathematics on the computer, just due to precision loss when storing numbers. So round if you want, or whatever, to whatever precision point you like. So scientific notation, scientific values are required, so on and so forth. You get the idea. Okay, and of course it put that number directly into its memory address. Okay, so let's step through this a bit more. All right, step over, and if I step over it one more time, it's now going to display. So if I click on output, there it is. Enter the resistance. The resistance. Let's do 5, 4. Sure, why not? 4, 5, 4. I don't know. I just ended up typing that. That works, right? All right, so let's take away from output again. It's going back to our numbers. And let's watch the I in current just materialize when we do this function. So let's step into this function. All right. And we have these values. This brings up a great point. How does that work? Well, you may know something. MV and NR are identical to what we had a second ago. Like, what? Yeah. So check it out. When we passed in their values, V and R, remember they were 30.01000002, and then we had, for R, it was 4.54. So we passed in our V, a voltage, and our R for resistance. And we come in here, check it out, our variables, and here MV and NR are those values. So what happened? Well, basically what happened was the value inside V got copied from its memory location up here, which is out of scope, so it's not showing you right now. But over here in this memory location, the value got copied and put into this MV memory location here. So you can see they're two totally separate variables in memory. They are not the same thing, but the value got copied from one to the other for the variables. This is what's referred to as pass by value versus pass by reference. When we were doing pass by reference, we were doing it here with the ampersand R, where we're passing stuff directly to the memory location of the variable. In this case, by pass by value up here, instead, we're passing in the value of V right here to copying it and putting it into the value for NV into its memory location. And so now MV has the same number. So there's some technical terms so people can tell what you're talking about for this. These are referred to as parameters. These are special variables where you can pass in values into these variables that are at the top of a function. And they're called parameters so that people will know you're talking about these particular variables versus other variables that might be somewhere in the function. So we have a special name for them when they're up here at the top like this, so you know what people are talking about without having to do a lot of description and confusion as far as that goes when you're talking to another programmer. So that's what the whole idea about it is for. And then we're going to do another one besides that here, and that is arguments. And that is the value that's being passed into the parameter. So, or aka the variables at the top of the function. So these are the arguments right here. These are arguments. These are values that we're going to pass to our parameters. So this is the parameter here, right? And the argument would be like V up here. That would be the argument being passed for the value to be passed into the variable, into the parameter in V. So that's what arguments and parameters are. Okay. Now we're going to take these two parameters and divide them by each other and return the value, and it's going to get passed by value back. So we're returning it, and it's going to be returned as a double. Awesome. And so when it gets passed back by value, it's stored in memory for this returned value, and then it's assigned to I afterwards. So I'll prove that. Just say step over one more time, and boom. And now we have a I that is 6.610132 blah 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 all the way out. So now I has been calculated and has a value stored into it, and that was returned by pass by value. So the value got returned, it was sitting here, and then it was said, okay, assign it to I versus saying equal to it. So, again, this is a double memory address type thing where we have the value sitting in here in RAM, and then it gets copied from there to the actual I when we said equal to. So that's what moved that value into I, was this equal sign right here within the computer. And so This gives you a good idea of how that is working and how that's happening. Essentially, that is how you compute this and assign it the value. And that gives you I. So printf, the current is %.3f amps ./n. Now, and then I. So what we're going to do is say we only want 3 floating point value here. So 0.610 is all we want, and we're going to drop the rest. Now this does not round. This just simply cuts it off right where it's at. So if you're looking for rounding or whatever, you need to actually round the number with a round function from the math library. That is what's required in order to make that round. So if I say step over, we get a display of this. And here we go. The current is 6.610 amps. And you notice you didn't get that huge long number. Why? Because I said 0.3f instead, %.3f, when we went to display it up here. And this is the reason why it got stored, got displayed with only 6.610 instead of 6.1013215859, 90309. You get the idea. So instead of having that whole long number, we only take it to 3 precision point decimal. Okay, and our program is done running. And that was the final output. If I say step over again, we come back to here, and now we're done. The program returned, blah, 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 it's done. So it's going to go ahead and stop it. Okay. One other thing to discuss here is, so that's an example of how you can step through this whole program and how it works. Okay. And that was a good breakdown of what was going on in the memory and going on with these variables and these different values as we step through it. Now note that if I didn't want to do integer, which is not a good idea to not want to do integer, I could do this instead, where I do it with a double. Someone asked me to show this. Alright, so I can do it this way. We're saying like if n is greater than or equal to 1, or, this means or. A single one is a bitwise or for doing bit operations on ones and zeros, a bit level. I'm not getting into that right now, it's more complex. But anyways, 2 of them is a whole or function. And then n here is less than or equal to 1. And n is not greater than or equal to 1.01, and n is less than or equal to 0.99. This whole thing is not. So if it matches either one of these, then not flips that around as the inverse of that. So it's like saying not true is false, right? And not false is true. Same idea. So how does this work? Well, you could sit there and memorize truth tables. I don't like that. I think it's just a lot of extra headache. But if you just talk it out in a logical way, this actually makes a whole lot of sense. So if I want to say if this is true or this is true, then, if either one of those is true, then the whole thing is true. And if they're both true, then the whole thing is true. And the only way you can get a false is if they're both false. So hopefully that makes sense. So if this one is true, or if this one is true, then the whole thing is true. But if this one is true and this one is true, then they're both true and the whole thing is true. But if both of them are false, then the whole thing is false. Alright. So same thing goes over here too. We have the same thing happening over here. And then what about and? Well, in order for and to be true, basically both of them have to be true, because I have to say if this is true and this is true, then the whole thing is true. And of course, any other combination other than that is going to be false. Think about it. If this is true and this one is false, then the whole thing has to be false, because you're saying and this one, right? It's like inclusive. You're not going to say like I want this one and then not mean the other one. So you're saying if this one is false and then this one is true, then the whole thing is going to be false. And if this one is false and this one is false, then the whole thing is false. So in the case of and, the only way for it to be true is if they're both true. In the case of or, the only way for it to be false is if they're both false. If you want to think of it that way. Every other combination is true on or, and every other combination on and is false, other than both of them being true. There you go. If you want to think of it that way. So this is one way to write it. A simpler way to write it, though, using less complicated structures here. Oh, I want to show you something too, by the way. These parentheses here make your life heavenly, because what this does is says what order you want to do the actual test conditions in. So I want to do this or here for this test condition, and then I want to do this or test condition also before I do this and. So this whole thing has to evaluate, and this whole thing has to evaluate, and then it has to be evaluated by the not. Then those two results can be evaluated with the and afterwards, at the very last one. So we set the order by using these parentheses, and that's what the magic and power of the parentheses are all about. So very, very important to use those and to do that. So make sure you use your parentheses with your functions, because it really, really matters. Not with your functions, but with your if statements. Yep. So if this whole thing ends up being true, then it will actually end up being false. Think about it, because of this not right here. And if the whole thing is false here, then it'll get flipped and it'll become true instead. So that's the way that works. That not there. Simpler way of saying it. Well, if n is less than or equal to 1.01 and n is greater than or equal to 0.99, we essentially get the same thing in logic versus the other one there that we have above. So these two do the same thing. This one above here does the same thing as this one here. You might be going, you gotta be kidding me. Nope, totally case. There's more than one way to solve a problem, but it doesn't always mean every way is the best way. There are some ways that are better than others. Obviously, this way is better than the one above it, because this requires less condition checks by the computer, so therefore it takes less computations, which means it runs faster. So not only is it shorter and easier to read, but it also executes quicker. So if you can make it simple and sweet and do the same thing, then you're better off, because it means it's going to execute faster when you do. So making something highly efficient is kind of important on that. And this would be done in place of this one with the int setup. But you would have to do this kind of range check. Remember, because of the floating point decimal errors? Remember how we ran this in RAM and we get these little values that get off by a little bit of precision? That's why you have to do this range. Because if you said 1, you can't be guaranteed you'll get 1. You might get 1.00001, or you might get 0.999999998, something like that. So because of that, you have to have this range check here for precision of the values. It's going to be very slight on this range check, so I can get away with this very minimal range check here on this. But again, this makes it obvious that this is a poor choice for menu selections, and the ideal thing to use is an integer. Not to mention, it's going to execute quicker, because again, this is shorter and takes less computations. So this is more efficient, this is faster, it runs quicker, it runs better, and you don't have the headaches of the range. So less headaches, easier to read, runs faster. Don't do it with a double or a float. That's how you do it, just don't do it. Alright. Awesomeness. Okay, cool. So with that said and done, there is our if statements. And that's all the different types of logic statements you can have. You can have greater than, not. Oh yeah, if you want to do a not equal to, by the way, it looks like this. Exclamation mark equals. That's not equals. So like, for instance, if I were to say it's not equal to 1, it's real simple. Bam, that's not equal to 1 right there. But I want to do an equal check on that. Okay, so that explains if condition statements. And what is going on here with our scanf and reading things into memory addresses and pulling data back, what happens in memory when it runs with a floating point, precision errors, all that good stuff. Now, what if we had something a little more interesting here? What if we added something called loops to this? And the way I'm going to do this is I'm going to modify this function here real quick. I'm going to change this to 4. Instead of solve for resistance, I'll say exit program. All right. Make your selection 1, 2, 3, or 4. Awesomeness. And what I can do is I can put this whole thing inside of a while loop, or I can return it. Instead of returning void here, it could actually return a value. So I think I'm going to do that instead. I'm going to return this value. It's going to say int here. We also need to add one more check. And that is, I want to add a check for if they put in 4 here. So I don't want to run another function. But I'll tell you what. Let's do something a little different instead. Instead of returning an int, let's return a boolean. That'll be more fun. Or we can do int. Let's do int. Yeah. Let's do int. Huh. Thinking of another programming language. Alright. Well then. Alright, I'm just going to put on a message. Printf, close parentheses, semicolon. Already have that part, right? Close parentheses here. And say something like exiting program now. Alright. I'm just going to let them know that we're exiting the program. Alright. And what I'm just going to return is the n here. So I'm going to say return n semicolon there. Alright, so n and control S to save. Alright. So I now save that. Okay, awesomeness. And we're good to go. So you might be going, whoa, dude. Well, hold up. Int. Compute. It's solving equals 0 semicolon. Alright, let's do something like that. And then we're going to say while solving is not equal to 4, continue loop. I'm just hitting tab to tab over that spacing. It's a really good idea to space out your code correctly, otherwise you're going to be unable to do it. Now I set this int here resolving to 0 because this check had to be not equal to 4 for it to work. Otherwise this menu code would never happen, right? And then I need to say solving is equal to menu here. So do we continue to loop? Alright. If we do, we continue to allow for different inputs until they essentially choose 4. So this is the way this works is while this condition is true, then the loop continues to work. The moment that it's false, then it does not work. So we're saying while solving is not equal to 4, we're going to continue to loop. What loop means is just going to repeat this code that's inside of this block here. Open close curly braces defines our block. And we're going to keep doing that code over and over and over and over again until solving is 4, essentially, because that's when it's false, because solving is always going to be true while it's not equal to 4. So the moment that solving is equal to 4, then it is false, and then it's going to exit out of that loop. Awesomeness. So with that all said and done, we're going to go ahead and run this and see what happens. And doesn't like something. Oh, right. After we do this, we have to come up here to our declaration and also set it to int. Yes, they have to match, otherwise, not good. And I totally forgot to do that. If I want, I can also line these up to make things easier to read. If you want to, like, do things in a very organized way, you can do that. Some programmers like to do that. It's good practice if you do, because it makes your stuff cleaner and more formatted, easier to read. Some people might not like this because it might make it a little more. But yeah, you could actually do it that way too, by the way. So that's legit. You can do that. And of course, you can see the benefit to this is that what is it doing? Why is it shifting the whole line? Whatever. Whatever. It's either going to be shifted forward or backwards, but not. That is weird. I don't know why it's doing that. Whatever. I don't care. It's whatever. But yeah, that's another way you can format this if you like. Just makes it easier to read. But to each their own. You don't have to do it that way if you don't want to. Okay, but anyways, that's why I was complaining, because I forgot to do that. And bam, there we are. So we have a choice of 1, 2, 3, or 4 now. I could say 1 here to run our program and enter the current, because we're solving for a voltage, right? So let's say it's 5. Let's say resistance is 4, or 3. 3 it is. Bam. And we got 15 volts, right? Now it's asking us again, which one you want to solve for. Let's do 2 now, all right? So for the voltage, just make it 40, and let's make a resistance 5. And then you can see the results of this is 8 amps there. Let's do 3 now. Voltage, they want again, let's do 40. Let's do this one at 2. And again, we end up with 20 ohms here. And then when I say 4 now, it says exiting program now, and then the program exits. So cool. This lets us run all our calculations that we need on different things, and it works over and over again in a loop. This is what a loop does for us. Pretty cool. Makes life a lot easier. There's no way to actually do this otherwise other than to use a loop. Because there's no way of predicting how many times someone needs to run a particular function or capability inside the program or repeat a certain set of code over and over again. It's conditional on whatever the need is as far as that goes. So you don't know ahead of time. Think about this. If you're going to a grocery store and you're buying groceries, right? You have no idea how many groceries each person is going to buy ahead of time. There's no way to code that. Each person is probably going to buy a different number of groceries all the time, different items, etc. So there's no way to predict that. So you have to have code that will be flexible to work in any condition and not just certain circumstances. So while these loops really help with that, lets you repeat code over and over again based on certain conditions. So that is the while loop, and that is how we can loop through some condition over and over again. So we'll look at some more programming here in structures in C in a bit, but this at least gives you an introduction to loops. Well, thank you very much. My name is Nate Nestler, and this is for Hyperactive Studios. Hope you enjoyed it.